ones that we use, I think, is relative, where it gives you the number of ticks that it has rotated relative to the very start when you power on the robot. And you can also change this later. In your code, you can always reset the encoders, and the unit it returns it to you is in ticks. And this is different for each encoder. I think the ones we use is 4,096 ticks per rotation, and this can be converted to number of rotations, which you can use for calculations later. So when you're controlling a motor, there's basically two ways you can do this. There's open loop and there is closed loop. Open loop, you can think of it like disconnected, like it's just a one-directional control. For example, you can set the voltage of your motor. So this would be an output command, but you would not get anything back from it. Or if you do get like an encoder value back, you don't use it. So that would be open loop. And closed loop, on the other hand, this one is, for example, you want to set the position or the velocity of the motor. And in closed loop, you output a command, then you receive sensory input, in this case through the encoder, and then the next output will be a modified command. And one example of this is a PID loop, which we're going to talk about later. So for open and closed loop, we use both of these in our robot. And the advantages to closed loop is that you can easily you just let the motor do its thing, and it can reach a set position or velocity, like even if the environmental factors are different. For example, if your drivetrain is going on like some kind of rough terrain, it's your motors are going to compensate for the fact that it's a different environment than what it's used to. Besides, and this is in contrast to open loop, where you're just setting a voltage. So the form of open loop that we use most often is called a PID loop. So PID stands for proportional integral derivative, and this is an auto-adjusting system. And yeah, this is the example I was using. If the wheel is on rough ground, if you run this loop, it's going to give your motor more power to run it at the desired velocity. And PID loops are manually tuned, which means each system is going to have a different set of PID constants. As you can see on the right, if you were using open loop, you would just be setting the reference signal. So this, for example, this would be like 5 volts. But if you're using closed loop, if you're using a PID loop, the signal that you're sending to the motor controller is actually some of these 3 curves, which we're going to talk about later. So this is a brief introduction to PID control, and we thought this video was just really good explainer. Wait, do I have to share my audio? Let me try this. Wait, Rohan or Dylan, do you guys know how to share audio, like on MS Teams?
I think there should be like a button at the bottom to share audio as well.
Oh, I don't think it works because you're on a Mac. So like if Dylan wants to do it, I think it would work.
Oh. Okay. Dylan, you wanna share the video? Because I don't have an audio setting. Thanks.
Yeah, give me a second, my headphones died.
I still can't hear audio.
Yeah, I'm not sure if it says it's set to record system audio. So.
Oh. Guess we could just link this video for all of you to watch after our presentation.
Yeah, that works.
Okay, let me reshare. Okay, so basically with a PID controller, you're trying to reach a set point. For example, we could talk about a motor reaching a current velocity, and it's going to use these three calculations to send an output to the motor that's going to help it reach your wanted set point. So it does this by, of course, looping. So every, let's say, 50 milliseconds, it's going to calculate the error using a sensor. So in our case with the motor, our sensor is going to be the encoder. And once it calculates that error, so that error is calculated with this simple formula. It's just the set point minus the current point that you're at. For example, if your set point is, you want to go 5 feet per second and your current point and your current velocity is 4 feet per second, then the error would be 1. And it calculates these three things. It calculates the proportion error. This is equal to the error. It calculates the integral error, and this is the sum of all the errors it has made. For example, if you're trying to reach a high value and it keeps trying to reach that value, but it doesn't reach it, this is when the integral part will come in handy, and it's going to contribute a large sum to your output signal. And this is the derivative factor. This is your error minus your previous error. And the output is just the proportion factor times a constant added to the integral factor times a constant added to the derivative factor times a constant. And these constants have to be tuned manually depending on what motor you're using, and just different. It's going to be different for each mechanism. So tuning PID, it's, as we said, it's going to be different, and we use PID for all of our motors, I think. We use it for our flywheel, our hood, our elevator if we had one, etc. And with PID, you have to remember you're going to be tuning a PID, a different PID for velocity and position, or for every different variable that you want to be controlling. So we're just going to go over tuning rules right now. This is going to be kind of hard to conceptualize because we don't have like a motor or any hardware to do this on, but here it is. You start off with setting Kp, or the P constant. You set this equal to 1 divided by the maximum set point. So this would be like the velocity that your motor goes when it's at maximum voltage, let's say. And you want to adjust this until it's able to reach any wanted set point, like with any amount of time. And because with Kp, it might take a long time for the motor to reach your set point, this is where you want to add a Ki, the integral constant. And you want to start this off at a very small value and slowly increase it until your motor can reach a set point relatively quickly. And then after you get this, sometimes you're able to reach a relatively smooth and well-functioning output with only a Kp, or maybe a Pi or a PD controller. So those are also useful. But if P and I is not enough, you can add a Kd value. And you want to increase this. You want to start this off small and increase it until you have a smooth progression to your set point. And now motor controllers have built-in methods for a PID controller, because the code itself is pretty simple, but we use it for all of our motors, so they have built-in methods for that. And they accept Kp, Ki, Kd as parameters so that you can easily set different set points in your code. And there's also a PID F controller, and the F stands for feed forward, and it's also sometimes called the bias. In a PID F controller, the output is the same as a PID controller plus a constant Kf. And this is needed if a regular PID loop cannot reach the set point. For example, with our flywheel last year, we used a PID F controller. Okay, Dylan, you want to go over this part?
Yep. Okay. So the robot class is extended from from what's called timed robot, which is provided from WPIlib, and that's just some Java stuff. If you guys want to go into the robot code, if you guys want to work on the robot code and you don't know Java, Java is a very good thing. Almost, I think it's mandatory. It's probably mandatory to know before working on the robot code. So get familiar with object-oriented concepts, because we use that a lot. But the basics are we get this thing called timed robot. and it has all these functions from robot init, which is called once we start up the robot, and then robot periodic, which called every period, wherever that's set by WPI regardless of what's happening. And then you have all the other stuff like autonomous, Tele-Op, and test. So we mainly work in the Tele-Op, and so in Tele-Op init, that's where we set up all our controllers, all the scripts that we need to run. In Tele-Op periodic, that's where we put usually the Tele-Op updater, which is, and if you can go to the next slide. So Tele-Op updater has a bunch of stuff that we add to controlling the drivetrain, the flywheel, etc., everything else. It receives input from the Xbox controller, and it updates all the subsystems, and it does that with a bunch of if statements and checks. So in the next slide, I believe we see how it does that. So Tele-Op updater, it has a few things for everything we want to control. The first one is we get the state of the controls. What's happening with the controls? Are we pressing the button? Oh wait, go back. Are we pressing the button that we assign to manually turn the turret left or right? We assign all these from the Xbox controller config, which is another class that we'll talk about later. But we set all these variables with all the states, and then, okay, you can go to the next slide now. And then we check that, and then we check if those variables are set to true or false. And we do something called set one states for our subsystems, and that pretty much just tells the subsystem what we want to do. So wants to manual left, wants to manual right, or wants to idle. We tell the turret that we want that. So this is just a bunch of, these are called enums, and you can learn about those later. But that's how we communicate with the turret that we want to, what do we want to do with it? And yeah, so Tele-Op updater, in the actual class, if you look in the class file, the first thing up towards the top you'll see is what's called a singleton design pattern. And that just makes sure that at all times there's only one instance of this class. And that's so we don't have two of the same class running because they might conflict with each other. So every time we access the class, it refers to the same instance. And from here, you can see both of these fields are both static, so you don't need to instance the class before you can access them. And then we store its own instance in a variable called instance. And it's a little confusing, but we use some ternary operators in there that pretty much say, if we have an instance of Tele-Op updater, we use that instance. If we don't, we create a new one and then we use that. So it basically just allows us to only use one instance at a time. Oh wait. Okay, wait, if you go back for a second. Wait. Okay, yeah. If you go into the next slide, Tele-Op updated, there's a bunch of stuff there too. There's the individual subsystem updates, which tells each subsystem that a specific time has passed. Accessing Limelight, controlling the vision stuff, the drivetrain code, moving around the robot and updating the dashboard. We all do that in the Tele-Op updater. So it's just a way to update everything that we use Tele-Op for. Okay, so Xbox controller config. This is a class that contains all of the actual controls that we want to use. So in this, we have a bunch of these methods or functions that we call. And these are set by us. So if we want to have a hood, we add a manual hood down or up or automatic or whatever it needs to be. The method names don't matter too much. But the main part is when we call these methods, it will check whether that condition is set for the controller. So for example, I believe raw access 1 is the one of the sticks, and it might be the x-axis, but we'll pretend. Oh no, left analog stick, vertical axis. Okay, so this just checks that if that specific axis on the controller is greater than 0.5, and if it is, return true. In case we want, if manual to check that stick, will say, oh, it's pushed down, let me return true, and then it will set that state. So yeah, it will, when the method is called, it'll check with the controller. And it's for me. So in case we want to completely redo all the controls, we need to search for every in Tele-Op updater. We just change this one file and it will change it throughout the entire code. And that's the Xbox controller config. And then Linus, do you want to present this or should I?
Sure, I'll do it. So we've talked before about state machines and how they're set with wanted states and system states. I think this is a slide I took from one of our previous presentations, but now we're going to actually go over an example of a state machine, so you can see how like all of these different parts of it play out. Okay. Okay, so you guys can see like the code, right? Am I on the right screen?
Yes.
Yep.
Yes.
So here we have a one of our classes. This is one of our subsystems. It's called Flywheel, and it extends subsystem base. And this is part of our this is actually part of our own library, which we call WarriorLib. So this is basically just a set of classes that we know we constantly want to use every year, and we update it regularly to contain code that can be reused, like basically every year. So that includes like our pure pursuit for our autonomous, as well as a lot of our base functions, such as subsystem base. Okay, so Flywheel, this is one of our subsystems, and you can see that it is a simple state machine with only 2 states and 2 wanted states. So as we've talked about before, Flywheel actually gets updated inside Tele-Op updater, and let's see if I can find it. Inside this update method, Flywheel gets updated. So that is this function over here, and every time the loop goes through, so I think it's 50 milliseconds or whatever we set it to, it's going to call this update method. So the first thing it does is it checks if we have a new wanted state or not. As we've talked about before, wanted states are also set inside Tele-Op updater. So we first check if we have a new wanted state or not, like if they press the button to run the flywheel, that would run the flywheel, and that would mean wanted state is changed. And inside our state machines, we sometimes have code that's like specific to what we're running. For example, every time we first run the Flywheel, we want to reset the Flywheel PID controller because it has a feed forward, and we don't want that to keep on running while our Flywheel is idle. So after it sets wanted state change and updates the previous wanted state, it runs a function based on its current state. So if we look at these functions, handle run is going to set the Flywheel velocity to set point. And if it's handle idle, it's just going to stop the Flywheel. After that, what it returns is the default state transfer. So, and it sets that equal to the new state. So this function is just an intermediate way of saying we want to run whatever function, whatever method that the current state is telling us to run, and then we want to return the state that it has to be in the next iteration. So in this state machine, for all of our states, it just goes to the default state transfer. So in the default state transfer, it's pretty simple. If the wanted state wants to run, it's going to return the Flywheel state run. If it wants to idle, it's going to return the Flywheel state idle. And it's important to know that the order of this is kind of like opposite to what you might expect. Because as you see in the update method, it first runs the state, and then it updates the wanted state. And then it updates the wanted state and the state for the next iteration. So it sets the state first, and then updates the state. So as you can see here, we have what I haven't explained is the set Flywheel velocity PID. This sets it to velocity set point. And this is another thing that Tele-Op Updater controls. It's going to update velocity set point based on wherever our robot is at. And the Tele-Op Updater really does all of the integration of the different subsystems and allows you to really focus on like the actual functions of the individual subsystems in here, and you integrate them inside Tele-Op Updater. Okay, so I hope that was helpful in like getting a view of what a state machine is useful for and like how you can write one yourself. Okay, I think that is also the end of our presentation for today.